It's down again, right? Concave down again. No inflection point there. And then 2, if you plug in 2, let's check it. What do we get? Is it? You think? I'm going to check it. I don't trust that it's. So let's see. If I plug in plug in 2, this becomes 2 cubed is 8, and then negative 8 minus 2 is negative on top. And on the bottom, 2 here is 8 minus 1 is 7 cubed. That's positive. So you get a positive over positive, which is positive. So it's concave up there. Whew. All right.
I just realized that you don't even have to rewrite a whole table again. You can build off it.
You could. You mean when we do our final picture? No.
Like, you know how you make that table?
Uh-huh.
Type deal?
This table?
Yeah, because, like, you know, you did the thing, all you gotta do is do it on top of it, and then do it again.
Oh, you mean the final version?
The final table, yeah.
Yeah, yes, but yeah, okay. Maybe. Maybe. You just have to be careful because on the final table, we put in all the critical numbers.
Right.
From the first derivative also.
Right.
So there's one on the first derivative that's not on this picture. Same number line. You could insert it in there. All right, so where is F? This has only taken us an hour. Where is F concave up? Where is F concave up?
From
negative infinity to cube root, yeah, of negative 2. Union. 1 to positive infinity. Where is F concave down? Cube root of negative 2 to where? Cube root of negative 2 to 1. We don't need to jump over 0, because 0 is part of our domain, right? So we can just go right out to 1. Inflection point? Where is it happening? Cube root of negative 2, right? Oh, how many inflection points do I have? You sure? Just 1. Here it changes, right? Here it changes, but 1's not in the domain. So we don't. So I only have 1 inflection point. It's this, and then plug that into the function, right? So it was what, negative 1.25? Is that what you had? For this? 1.259. So we got to plug that into this right here. So cube it, subtract 1, and then I'm trusting you can plug numbers in. Whoa, what? That's not what I got. I got 0.42-ish. 0.42? Okay, that's what I've got. Somewhere around 0.42. I'm going to scrap this. I'm going to write that as a decimal. Negative 1.259 and then 0.42, like that. That okay with you for inflection point? My goodness, right? I mean, this is a lot of work. All right, we have all the information. Now we're going to start the graph. So to start our graph, we're going to start. This is not the graph. Remember, this is where I'm going to write those 3 rows. What do I put on this number line? All the critical numbers. All right. So from the first derivative, what were our critical numbers from the first derivative? And I know 1 was there. I know it was the cube root of negative 1/2.
There was
negative 0.79.
0.79, yeah, okay. All right, I have that. Those are the only two from the first derivative, right? From the second derivative, it was negative 1.259, and then there was also 0, right? And there was 1 also. I'm just listing out my critical numbers here. That way I can put them in the right order here. So the biggest negative number I have is this one. And 0 I have, so let me try and make this look good. Here's 0. 1, I'm going to put 1 about right here. I'm going to put negative 1.259 here, and then negative 0.79 here. Is that all right? Then I draw straight up from these so I can create 3 rows. F double prime, F prime. Well, what does the first derivative tell us? That was, I don't remember.
First derivative, what side?
You can go back and look at where you said it was going up and down. Like, where was F increasing? You wrote it in interval notation.
Yeah.
F was increasing where?
Negative infinity
Of cube root of 3, so up to here. So it would have been increasing here and here. And then it went down. Yes?
to down from that all the way to cube root of negative 1/2 all the way down all the way to 1.
To where?
To 1.
To 1. And then up again after 1?
No,
Or-
mine was down. Still.
Down again still? Yeah, that's right. It was down again like that. Does everyone agree? All right, second derivative, I think I can remember this. No, maybe not. It was concave up initially, right? It was up here to the left of cube root of negative 2, and then it was down until I get to 0, right? Down until I get to 0. And then
It was down after 0.
down after 0,
Yeah, all the way until you get to 1.
and then when I get to 1, it switched to up. You all double check, because I don't have that information in front of me. Does that look right? Okay. And now you paste these two pieces together to create the top box, right? So which side of this smile am I on, left or right? The right side, because I have to go up. So it's going to look like this. And then which side of this frown? Left side, because you have to go up. Which side of this frown? Right side. Which side of this frown? Right side again. That's trouble right there. Here? Right, like this. Left. Can y'all double check that table? Does everyone agree with that table?
Why do you say trouble?
Because of what's happening at 0. I have an issue with this. It's no, the asymptote's at 1.
Oh, 0 cannot exist.
0 is my x-intercept. Okay, well, we're about to find out, but I have I'm concerned right now.
Are you doubtful?
I am very doubtful right now. Something looks off. Okay, here we go.
Finally graphing.
Hmm?
Finally graphing.
Yeah, we're going to start graphing. So we're going to start putting these points in. We know at 0 we have 0, right? We know at 1, what do we have? Vertical asymptote. We know at 0.79, negative 0.79, right? What was the y value at negative 0.79? This was our local max. 0.53. And then what was this number? 0.4 something? Right? 0.42. So let's say right here is 0.5. Okay, can we say that? Then here at this value, negative 0.79, you said it was what, 0.5 something or 0.53? Do you agree we'll be up here? Yeah? And then at negative 1.259, we're going to be at 0.42 something, somewhere around here. We good? There's some other pieces to my graph that I have not included. How about the horizontal asymptotes? We know my graph flattens out over here, right? And we know the graph flattens out over here. Yeah? Let's see if we can draw it from this. I still think we have a problem. But let's just go with this. All right, from this point right here to the left, it has to look like this, right? So can you all see it? I've got to go flatten out towards this. It's going to look like that. That okay? Now from here to here, it's got to look like this. So I have like that. And then from here to here, I've got to look like this, right? And this is where I felt like I had trouble, but now I think we're okay.
Why did you think we had trouble?
Because we have to keep this shape, right? So all I'm going to do is just keep it concave down, like this. Oops. Whoa, my marker. But the problem is because I've come in this way, I've got it, here's my vertical, it's going to basically keep on going down and moving over and just dropping down to negative infinity. Do y'all see that?
Yeah.
Like this.
Can I make a suggestion?
Yes.
Make it look like to represent it more if you drop the negative 5 to 0.5 just a little bit lower.
Yeah, oh yeah, I could do
It's
that.
not really making a real big hump.
Yeah, I know. Yeah, my scale's off.
Easier to
My scale is off, but I mean, it's still giving us the important information, which is what we want. So that's okay. I'm all right with that. But we still have to figure out what's happening over here. So how do I draw this? It has to look like this, right?
Okay, so in between the top and bottom.
Okay.
You have to do a test.
But is it up here or down here?
You have to do a test point to see if it's positive.
You would think test point maybe, right? To figure out if it's above or below, but you can tell by the shape it can only be one of the two.
It can only be on top.
It can only be on top. Because it has to go, what, vertical asymptote, and it has to flatten out towards this. The only way you could do that on this side is if you went this way, right? And that would be opposite of what this is. Well, it wouldn't be the same. So it's got to go up like this and down like that. That's it. Okay, that took us about an hour. It took us about 70 minutes to do that.
And you know what you're doing.
I don't know, for a second there I didn't feel like I did.
You're just going to wing it?
Okay,
Yeah, can you just jump to the one that's on the closed interval?
yeah, let's do the trig one. Here's what my plan is, okay? My plan is to do 2 problems in this class. I don't know if I'll have enough time. My class tomorrow, I'm going to do 2 more that are different than the ones I do today. So if you can go watch theirs, and I'm going to tell them to watch yours. I had a problem with their camera the other day again, on last Thursday.
Please tell me that your microphone's been on the whole time.
My mic is on, yeah. Yeah, it's more the contrast on the video, it's kind of washed out, but you can kind of make sense out of what I'm doing. Like you can see it, just not real clear. All right, so let's do one here that has some trig in it on a closed interval. Let's see what we can do in the next 25 minutes. That's all we have. So I'm going to move a lot faster. Let's go with y equals, I'm going to call it f of x instead, is 1/2 x minus sine x. And this is on the interval 0 to 3 pi. Notice that's not a closed interval, right? Because I don't have brackets. That's an open interval, 0 to 3 pi. So we want to draw this picture, sketch this, just on that interval.
So you're basically limiting.
I'm limiting the amount of work you're going to have to do by doing that.
Which number is this book?
In the book, this is number 31. Okay, domain is all real. Well, it is all real, but we're restricting it, right? So first thing, domain for this particular function, because they gave it to us, 0 to 3 pi. All right, second thing, x-intercepts, y-intercepts, right? Was that it? Yes. How about the x-intercepts? Can you find any x-intercepts? You have to set the function to 0, right? Ooh, that doesn't look good. 1/2 x equals sine x is the, maybe you could do that. Can anybody just give me a solution by what we call inspection? Just by looking, can you just kind of do a smart guess as to what one answer is? 0, right? Won't 0 work? What's sine of 0? 0, and 0 on both sides works, right? So x is 0 works. But other than that, that's not something that we can solve easily. So this is where I was saying, when you look at it, you're like, okay, well, can we solve it? That one you can do just by looking, but other than that, that's not an easy thing to solve. Now, if it was sine x equals 1/2, then of course we could do it. But it's 1/2 x. Not so easy. Maybe I can convince you of the solutions by looking at this. Here's sine out to 3 pi. Do y'all agree that's sine out to 3 pi? Because out to 2 pi is here, right? That's sine out to 3 pi. What does 1/2 x look like? The left side of this equation? If I ask you to graph 1/2 x, what is it? A line? What's the slope of the line? 1/2? So if I start from this point and I draw a line, like this, it looks like, of course they hit here, right? But they may hit again somewhere. They might. And if it's a low enough slope, it might even hit multiple times. But I'm not going to be able to find those solutions. Not easily. So I'm just going to have to wave my hands at this one. Say x is 0 is the best I can do right now. All right, so I move on to the y-intercepts. Are there any y-intercepts? Plug in 0, and if you plug in 0, you get 0. So it's the same as the x-intercept. Third step, symmetry. I'll leave that to you. You can check it yourself. See if it's even or odd or neither. I'll leave it to you for time's sake. For fourth one, we want the asymptotes. Do we have any vertical asymptotes? If I put VA, is that okay? Everyone understand I'm looking for vertical asymptotes? Do you ever have any division by 0 in this? No. So you don't have any. None. Okay, how about horizontal asymptotes? You have to let x go to infinity, don't you? In negative infinity? All right, so what's the limit as x goes to infinity of the function 1/2 x minus sine x? It's infinity minus sine of infinity. Sine of infinity is not infinity. You're saying the whole thing is still infinity. Is that what you're saying?
Well, sine infinity is not infinity.
No.
Because it'll go to 0 and then back to...
It oscillates, doesn't it? So this is bounded, isn't it? As I go out to infinity, this just keeps oscillating back and forth between -1 and 1. And this guy's just getting huge, right? So the most this could do is like subtract or add, right, 1. And that's not going to affect infinity. So that thing's going to infinity, isn't it? How about if I go the other way? Go to negative infinity. Now that's going to negative infinity, isn't it? And this doesn't make a difference. That oscillates. So this goes to negative infinity. What does this mean in terms of our picture? As we go out to the right, this thing goes what? Up forever. As we go out to the left, this thing goes down forever. But keep in mind, we're not even looking at forever in each direction, are we? We're just looking between 0 and 3 pi. I only did this just because I want you to see how you would approach it, all right?
So if we have an interval.
Then there's no need for horizontals. Yeah. All right, fifth step. What's fifth? Where it's going up and down, right? Are we there now? Okay, derivative of this. So derivative is 1/2 minus cosine x. Where's this derivative 0? That's where 1/2 minus cosine x equals 0. Just move things around. This is just saying where is cosine 1/2, right? Where's cosine x 1/2? What?
You drop negative.
No, but you have to divide it by the negative 1.
I just added cosine to both sides. Add cosine. Add. Is that okay?
No. Simple math is singular.
So where's cosine 1/2? We go back to our unit circle. Cosine is which coordinate?
The x coordinate.
The x coordinate. And so that's going to happen here and here, right? So this happens when x is pi over 3. And then we keep coming around, and what's this one? Five pi over 3. And can I keep coming around? Yes, because I can go anywhere between 0 and all the way around 2 pi to 3 pi. So I can come around to this one again. What would that one be? Good, 7 pi over 3. And that's the biggest you could go. You couldn't keep going because that would go past 3 pi. That good? 3 critical numbers. They're all in the domain. I need to put them on a number line. And let me do this. I'm going to go 0 to 3 pi, like this. Because that's where I'm stuck between, right? I'm not allowed to look outside of that. Let me see if I can't put these in here nice and clean. Here's pi. Here's 2 pi. Y'all see what I'm doing? Splitting up into 3 equal sections. Pi over 3 would be here, wouldn't it? That's a critical number. 5 pi over 3 would be here, right before 2 pi. And then 7 pi over 3 would be right there. Y'all still good? Do you see your test points? Where they have to be? I need one here. So what, pi over 6? Something between here and here? Let's go with pi. Something between here and here? 2 pi. Something here? I have to be between 0 and, let's see, that's pi, that's 2 pi, here's 3 pi, right? This was 7 pi over 3. Couldn't I go 8 pi over 3? Wouldn't 8 pi over 3 put me here? I could do that. All right, let's see if you can plug these in as fast as I'm about to. All right, you ready? Y'all please ask me questions if you don't understand what I'm about to do. This is the derivative, right? I'm plugging in these test points into that derivative. And what I want to know is whether or not it's positive or negative, right? Okay, so pi over 6. The way I'm going to do this, I'm not even going to plug pi over 6 in there. I'm just going to think about it right here. Here's pi over 6, right? What's cosine of pi over 6? Root 3 over 2. If I take 1/2 and I subtract root 3 over 2, what would I get? Positive or negative? If I take 1/2 and subtract root 3 over 2, then that's the same as 1 minus root 3 over 2, right? Combine them. What's 1 take away root 3? It's negative, isn't it? Because root 3 is bigger than 1. So this is a negative number. Got it? So that's negative, which means my function's doing what here? Going down. Okay, now let's plug in pi. All right, so now I'm going to come over here to pi. What's cosine of pi? Negative 1. What's 1/2 take away negative 1? That's 1/2 plus 1, which is positive. So it goes up. Local minimum. Now plug in 2 pi. So if I come around to 2 pi, what's cosine of 2 pi? 1. What's 1/2 take away 1? Negative. Goes down. 8 pi over 3. That's right here. What's cosine of 8 pi over 3? Negative cosine. Negative 1/2. What's 1/2 minus negative 1/2? Positive 1/2. Or positive 1/4, right? No, hold on. Positive 1. Sorry. It is 1/2 plus 1/2, which is 1. It's positive though. So it goes down, up, down, up. Local min, local max, local min. I'm almost out of time. I got to go to the second derivative. Can I move on? We've got all the information we need. We're going to have to plug these points in. Pi over 3, 5 pi over 3, 7 pi over 3. We're going to have to plug them into the original function. I'm going to do that later. Normally I would do that now, wouldn't I? Yeah. Okay. So I'm off to the 7th step here. What's the second derivative of this function? That's actually a really nice function, isn't it? Sine x. Because the 1/2, derivative 1/2 is 0. Derivative of cosine is negative sine, but it was already negative, so sine x. Nice. Where is the second derivative 0? Well, that happens when sine x is 0. And this one is going to be real clean, right? Where is sine 0 on the unit circle? 0, pi and 2 pi and 3 pi. So this happens at 0, pi, 2 pi, 3 pi. So I get to split my number line up. I think I'm going to leave this one here because I'm going to refer to it in a minute. I'm going to do that part up here. I have 0, 3 pi, here's pi, here's 2 pi. Splits it up. And check this out. I'm not even going to do a test point. I'm not even going to do a test point. I'm just going to think about it. My derivative is sine x, right? You could draw it, yeah. Look at between 0 and pi, sine is the y coordinate, right? Yeah. Sine is the y coordinate. If you're anywhere between 0 and pi, your y coordinate must be positive. That means I'm concave up here. If you're between pi and 2 pi, that means between here and here, your y coordinate, which is sine, right, is negative. And then, of course, between 2 pi and 3 pi, same thing as between 0 and pi. We have 2 inflection points. Questions? All right. I'm going to keep that there. I'm going to try and draw this. 0, 3 pi,
You're not even going to make your
2 pi. No, I'm making my table right here. Pi. But I'm doing a fast table. And it's actually pretty bad. Here's f prime, here's f double prime, and here's f. I need to label all the critical numbers on here. So pi over 3, I need that in here. I was missing that one. And 5 pi over 3, which was right here. And then 7 pi over 3 which was right here. It goes down right here, and then up until I get to 5 pi over 3, and then down until I get to 7 pi over 3, and then up until I get to 3 pi. It's concave up between 0 and pi, concave down between pi and 2 pi, concave up past 2 pi. I know I'm going fast, but do you all follow what I'm doing at least? So tell me what you're going to have in those top pieces. What's the top left? Left half of the smile? Right half of the smile.
Left half of the frown.
Left half of the frown.
Right half of the frown.
Right half of the frown. Left half of the smile.
Right half of the smile.
Right half of the smile. We're almost there. I've got 10 minutes. We're going to be able to get a final picture here. I'm only graphing this between 0 and 3 pi.
So the one on the closed interval is literally just the same.
We're
The
not,
domain is given to you.
yeah, we're not going to actually plug in 0 and 3 pi though, because we're not allowed to. Why aren't we allowed to plug these two in? They're not included in the domain. So I'm going to plug in right now. Remember, if we would have actually done the tables correctly over here, we would have, like at the local min, we would have found it, right? Local max, we would have found local min. So we would have plugged all these values in. I just saved that for the very end. So I'm about to take all of these right here, this, and this. I'm going to plug them into the original function. So maybe you can help me with that. I'll need a calculator. Let's try f of pi over 3. So that's going to be 1/2 times pi over 3 minus sine of pi over 3, which is pi over 6 minus what's sine of pi over 3? Root 3 over 2, right? Sine is the y-coordinate. So root 3 over 2 here. I'll need that. I'm going to go through all these first, and then I'm going to actually go and get them on the calculator. What's f of pi? That's my next one. So it's 1/2 times pi minus, what's sine of pi? Is 0. So it's just pi over 2. Right? And then the next one I need 5 pi over 3, which will become 5 pi over 6 when I multiply times 1/2 minus, what is sine of 5 pi over 3? So where is 5 pi over 3? Isn't that right here? Is that negative root 3 over 2? But I'm subtracting it, so minus root 3 over 2. It'll become plus root 3 over 2 when I put them together. Two more. F of 2 pi is going to be, when I hit that with 1/2, it's just pi. And then I'm going to do minus, what's sine of 2 pi? 0. That's just pi. Wait a minute, hold on. 5 pi over 3. Yeah, 7 pi over 3 is up here. Sorry. 7 pi over 3 is up there. So I'm moving on to my last one. When I plug in 7 pi over 3, I get 7 pi over 6. Getting sloppy. 7 pi over 6 minus what's sine of 7 pi over 6? Root 3 over 2. All right, so I need to do these on my calculator. Pi over 6. Do you have them all? Okay. We're going to trust Bailey here. All right. Okay, so let's go. You did pi over 6 minus root 3 over 2 and got what?
Actually made a table.
Okay, good.
So that one should be negative 3.3424.
3 point.
Negative 0.3424, sorry.
Okay, that's fine. Okay, and then pi over 2, 1.5 something? 5.7? Yeah.
It's showing me decimals, so I only have
Do you get 1.57?
Yes.
Okay. And then at 5 pi over 3, what comes out here? 3 point, is that what you got?
Yeah.
484, all right. And then pi, we all know that that's 3.14. And then last one, 7 pi over 6 minus root 3 over 2. 2.80? We're going to know if these are right when we try and draw it. If one of them is in the wrong place, it's not going to work. So let's just paste these in here real quick. What's the biggest y value I get according to this? 3.4, and the smallest I get? Negative 0.34. So you know what? I mean, when I draw my y-axis in here, I want to make sure I go up to maybe like 3. I don't know, is that high enough? Let's make that 4, okay? So that's 2, that's 3. So is that okay with you? Something like that? And then negative 1, negative 2, negative 3, something like that. All right, so at pi over 3, where are we? I'm going to do this in a different color. At what? Negative 0.34? So something like this. At pi, we're at 1.57, something like that. At 5 pi over 3, we're at 3.4 something. At 2 pi, we're at 3.1, so it's a little lower. At 7 pi over 3, 2.8, a little lower. And that's good. You got all that? Now let's put them together. What else did we have? Did we have an x-intercept? Did we have an x-intercept?
Yeah.
At 0, right? So we know we go to this, right? Now I'm not allowed to draw that on my picture. We could do an open circle here, good. And I know that I could like connect those two together with this piece right here. So it's going to do like that. Do y'all see that? My little left side of my smile. Then from here to here, right side of the smile. And then from here to here, left side of the frown, inflection point there, right? That's an inflection. I'm coming up to a local maximum. Coming down to another inflection, right? Local minimum. Right side, going up. And it's going to be a circle somewhere over there, but that's it.
So what's different from these is the one we did last class, right?
Yeah, the asymptotes in the in this problem, that really didn't factor in.
So the way that you're setting up your tests is like, are these,
It's a mix.
I know, but these 4 that you gave us, is that all the graphing that we're going to have to do? As far as like taking it and doing different derivatives. You know what I mean?
Well,
Basically, are we going to have to do any of that work?
Are we going to have to do
Like
any
these
of
problems?
this like on the test?
on this table, you might have one, but it would be very, very basic. A little polynomial, just to show me
So if
you
we
know
can
how
get
to do
through
it.
that, then we're fine.
You should be, yeah. Okay, so that's it. I mean, I was only able to barely get through 2 examples here. What's your question?
For the test part, if it's on a closed interval, are you wanting global maxes and global?
Nope, I want you to sketch it on that interval. Yep. Next class, optimization, word problems. Please make sure you watch the video for 4.5. Everyone okay with that? All right. I don't want to have a quiz on 4.5 and people not be ready for it.
All right, cool. Thanks for the heads up.